the chaotic beauty of coalescence. Join us as we explore the hidden complexity when two droplets merge. When two droplets approach each other, what seems like an instant merge hides an incredible universe of physics happening in microseconds. Let's start by understanding what actually happens when droplets merge. Here's a question. When you see two water droplets merge, does it happen instantly? The answer is no. When we use ultra-fast cameras filming at millions of frames per second, we see a hidden world of dynamics. A tiny liquid bridge forms between the droplets, growing rapidly through complex fluid dynamics. This bridge is the key to understanding coalescence. Let's examine how this liquid bridge forms and grows. The bridge radius grows as the square root of time initially. This is written as r of t scales, with t to the power of 1/2. But why does it follow this specific scaling law? Let's dig deeper. Two forces compete. Surface tension pulls the liquid together while inertia resists rapid changes. Their balance creates this square root scaling. Surface tension is the driving force behind coalescence. For water at room temperature, surface tension gamma is approximately 0.072 newtons per meter. Surface tension creates a pressure difference across curved surfaces, pulling the droplets together. The pressure difference equals gamma times the sum of inverse radii. This is the Young-Laplace equation. These pressure forces point inward, squeezing the liquid and driving the coalescence process forward. Viscosity introduces another layer of complexity through a dimensionless number. The Ohnesorg number equals viscosity divided by the square root of density times surface tension times radius. What does this strange number actually tell us about coalescence? It compares viscous damping forces to the combination of inertia and surface tension. It determines the character of coalescence. When Ohnesorg is much less than 1, coalescence is inertial and violent. When much greater than 1, it's viscous and smooth. Near 1, we see transitional behavior. Let's work through a real numerical example with water droplets. Consider water droplets with radius 1 millimeter and density 1,000 kilograms per cubic meter. Water viscosity is 0.001 Pascal seconds, and surface tension is 0.072 newtons per meter. Calculating the Ohnesorg number, 0.001 divided by the square root of 1,000 times 0.072 times 0.001 gives approximately 0.0037. This small Ohnesorg number means water coalescence is highly inertial, with dramatic dynamics. Now, we reach the fascinating part, why simple scaling laws break down. Does that square root of time scaling we mentioned earlier always hold true? No! As the bridge grows, the physics changes and multiple distinct regimes emerge. Early on, we see square root scaling, but as the bridge grows larger, it transitions to linear growth. The physics fundamentally changes. Let's examine the early inertial regime in detail. In the inertial regime, bridge radius equals the square root of gamma over rho times the square root of time. The characteristic capillary velocity is the square root of gamma over ratio r, approximately 0.27 meters per second for millimeter water drops. Liquid rushes inward from all directions, driven by surface tension gradients. The flow is radially symmetric and highly dynamic. As the bridge grows, viscosity becomes more important. In the viscous regime, radius grows linearly with time, gamma over mu times t. When exactly does this transition from square root to linear growth happen? The transition occurs at a characteristic radius, mu squared over rho gamma. For water, this is approximately 14 nanometers, an incredibly small scale. Droplet geometry adds another layer of complexity to coalescence. When droplets have different sizes, the flows become asymmetric and more complex. The bridge forms off-center, and fluid flows are no longer radially symmetric. This breaks the simple scaling predictions. Coalescence can trigger surprising oscillations and instabilities. After the initial merge, the combined droplet doesn't settle immediately. It oscillates vigorously. The oscillation frequency equals 1 over 2 pi times the square root of 8 gamma over rho r cubed. The droplet alternates between prolate and oblate shapes, dissipating energy through these oscillations until it reaches equilibrium. For a 1 millimeter water droplet, this frequency is approximately 1400 Hz, well into the audible range. Sometimes coalescence creates tiny satellite droplets. Why do these tiny satellite droplets sometimes appear during coalescence? The answer lies in instabilities that develop during the collapse of the liquid neck between droplets. The neck can pinch off irregularly, creating tiny satellite droplets that fly away from the main merged droplet. Another dimensionless number governs coalescence, the capillary number. The capillary number equals mu v over gamma, comparing viscous stress to surface tension. This number determines whether droplets will actually coalesce or bounce apart. At low capillary numbers, droplets easily merge. At high values, viscous forces prevent coalescence, and droplets bounce apart. Let's connect this to something familiar: pouring cream into coffee. When you pour cream into coffee, you can watch tiny droplets form, merge, and create beautiful swirling patterns. This is coalescence in action. Droplets merge in a cascade, each coalescence event triggering flows that cause more mergers. The fluid dynamics from each merger create currents that bring more droplets together, creating a cascade effect. Coalescence happens across an enormous range of timescales. The characteristic coalescence time equals the square root of ρHOR cubed over gamma. Let's look at numerical examples across different scales to see how fast this really is. For a 10 micrometer droplet, coalescence takes about 4 microseconds. For a 1 millimeter droplet, it takes about 4 milliseconds. And for a 1 centimeter droplet, about 40 milliseconds. The Reynolds number reveals whether coalescence is smooth or chaotic. Reynolds number equals ρVr over mu, comparing inertial to viscous forces. For a 1 millimeter water droplet, Reynolds number is approximately 270. This high Reynolds number means coalescence is turbulent and chaotic, not smooth and laminar. The flow becomes chaotic, with swirling vortices and unpredictable patterns during the coalescence process. Now we can understand why simple scaling laws fail to capture the full story. Multiple physical effects compete at different length and time scales, each dominating in different regimes. Surface tension, inertia, viscosity, and geometry all play roles. Their relative importance changes as coalescence progresses. The transitions between different physical regimes create the beautiful complexity we observe. Coalescence appears everywhere in nature, from clouds to cells. In clouds, tiny water droplets grow into raindrops through countless coalescence events. Cell membranes fuse during critical biological processes, like fertilization and neurotransmitter release. Many tiny cloud droplets coalesce over time, eventually forming large drops that fall as rain. Understanding coalescence has crucial industrial applications. Industries need to control coalescence in emulsions, sprays, and foams to optimize their products. Inkjet printing depends on precise control of droplet formation and coalescence for high-quality output. In printing, droplets must land and coalesce in precise patterns, requiring deep understanding of these dynamics. The full mathematical description involves the notoriously difficult Navier-Stokes equations. The Navier-Stokes equations with surface tension terms describe fluid motion during coalescence. This is one of the hardest problems in mathematical physics. No general analytical solution exists for these equations. We must rely on numerical simulations and experiments. Modern supercomputers can simulate coalescence, revealing details impossible to observe experimentally. Let's examine the energy transformations during coalescence. Surface energy changes equal 4 pi gamma times the sum of initial radii squared minus final radius squared. The reduction in surface area releases energy that becomes kinetic energy of fluid motion and eventually heat from viscous dissipation. For 1 millimeter water drops, the energy released is approximately 10 to the negative 9 joules. Energy flows from surface energy to kinetic energy as the bridge forms, then dissipates to heat through viscosity. How do scientists actually study these ultra-fast events? High-speed cameras can capture millions of frames per second, freezing the rapid coalescence process. Laser techniques can reveal the internal three-dimensional flow structures invisible to normal cameras. Cameras capture the merging droplets while computers analyze the images to extract quantitative data about bridge growth and flow patterns. Coalescence involves mathematical singularities that fascinate physicists. Here's a deep question. Is there a true mathematical singularity at the instant of first contact? At the molecular scale, quantum and thermal effects smooth out what would be a mathematical singularity. The minimum meaningful radius is on the order of nanometers, where continuum fluid mechanics breaks down. The inverse radius appears to diverge, but is bounded by molecular effects. Molecular effects smooth out this potential singularity, making the physics well-behaved at all scales.